You'll frequently be asked to deduce the molecular structure of unknown compounds given only their molecular formula, various spectral data, and sometimes chemical reactivity data. Specifically, we'll be reviewing how to calculate degrees of unsaturation given a molecular formula, uh, mass spectrometry, infrared spectroscopy, and nuclear magnetic resonance spectroscopy in a series of videos. In this first video, we'll begin with degrees of unsaturation calculations and IR. Degree of unsaturation is a ring or a double bond. Alkanes, totally saturated molecules, have no rings, no multiple bonds. They are said to have 0 degrees of unsaturation. If a molecule has either one ring or one multiple bond, it is said to have 1 degree of unsaturation. If it has 2 rings or 2 multiple bonds, or if it has 1 ring and 1 multiple bond, it is said to have 2 degrees of unsaturation, etc. You can get the degrees of unsaturation for a particular structure by looking at its molecular formula. There's different ways of doing that, but a simple way would be to compare the molecular formula of the compound that you're investigating with the molecular formula of the alkane, the corresponding alkane with the same number of carbons. That's illustrated below by comparing the structure and molecular formula of ethane, totally saturated molecule, 0 degrees of unsaturation, with ethylene. This has 1 double bond, 1 multiple bond. Its molecular formula is C2H4. If I compare C2H4 versus C2H6 and subtract C2H4 from C2H6, I get 1 molecule of H2, which is 1 degree of unsaturation. So this is a quick way of doing the calculation. Another example would be to compare the structure and molecular formula of acetylene or ethyne versus the totally saturated C2 compound, ethane. Subtract C2H2 from C2H6, the difference being 4 hydrogens, which equals 2 molecules of H2, which is 2 degrees of unsaturation. A ring is also a degree of unsaturation. If I compare pentane versus cyclopentane, cyclopentane has the molecular formula C5H10. If I subtract that from the totally saturated C5 compound, C5H10, I get 1 molecule of H2, which is 1 degree of unsaturation. Now, when you're asked to solve structure elucidation problems, you're frequently going to be given the molecular formula along with spectral data and maybe even some chemical reactivity data. Before you do anything else, the first thing you should do is calculate the degrees of unsaturation for that unknown compound before you dive into the spectral data, because if you know that the molecule has, say, 1 degree of unsaturation, as you start to interpret the spectral data, you'll know what to look for. You can immediately start to look for information to help you identify what that 1 degree of unsaturation might be. You'll frequently encounter molecules with structures that have, in addition to carbon and hydrogen, oxygen, halogen, or nitrogen, and you have to deduce their structures. How do you calculate the degrees of unsaturation in that case? For molecules that have oxygen, for example, C6H12O, you can just basically ignore the oxygen for the purposes of the calculation. So something with the molecular formula C6H12O, for the purposes of the calculation, you can treat it as C6H12. For example, if I took a molecule that has 1 degree of unsaturation and it has an oxygen, if I snipped out this oxygen and connected these 2 carbons together, I've removed the oxygen, but I've not really changed the degrees of unsaturation by doing that. So therefore, you can just pretend that the oxygen isn't there in the calculation. So I would compare C6H12 versus the totally saturated C6 molecule, which is C6H14. and I get 1 degree of unsaturation. When you have a halogen in the molecule, since a halogen is monovalent, it acts just like hydrogen. For the purposes of the calculation, you can treat the halogens in the molecule as hydrogens. So a molecular formula of C6H11Br, for the purposes of the calculation, can be considered to be C6H12. So I basically substituted the bromine for a hydrogen. I do the calculation, and again, I get 1 degree of unsaturation. And you can see by replacing this bromine with a hydrogen, I've not changed the degrees of unsaturation in this molecule. When you have nitrogen, because nitrogen is trivalent, I have to actually subtract N and H from the molecular formula. So C6H13N, for the purposes of the calculation, would be C6H12. Again, compare that to C6H14, do a subtraction, you get 1 molecule of H2, which equals 1 degree of unsaturation. Let's do a few practice problems. The molecule that has the molecular formula C4H8, how many degrees of unsaturation would that have? Well, I'd have to compare it to the totally saturated C4 compound, which is C4H10, and the difference would be 1 H2, 1 molecule of H2, which is 1 degree of unsaturation. So that compound could be, for example, something that has a multiple bond, or it could be something that has 1 ring. And these are just some examples. There are others you could draw. How about C3H6O? Well, we know that we can just, for the purpose of the calculation, pretend the oxygen isn't there, compare C3H6 versus the totally saturated C3 molecule, subtract, I end up with 1H2, that is 1 degree of unsaturation, and structures that would fit that description could be these carbonyl compounds, or it could just be a molecule that has a ring. So these have 1 double bond, this has 1 ring, that's 1 degree of unsaturation. What about a molecule that has the molecular formula C4H9N? We have to subtract N and H from that. For the purposes of the calculation, I use C4H8, subtract that from C4H10, the totally saturated version of C4, and I end up with 1 degree of unsaturation. And some examples of a molecule that has 1 degree of unsaturation with a nitrogen in it could be this alkene, aminoalkene, or it could be this cyclic amine. All right, some more practice. As we go through this, it's a good idea for you to stop the video and see if you can work out the problems before I present the solutions on the screen. All right, aspirin has the molecular formula C9H8O4. For the purposes of the calculation, I pretend the oxygens aren't there, and I compare C9H8 versus the totally saturated C9 compound, which would be C9H20. That would be 12 hydrogens, which equals 6 H2s, which equals 6 degrees of unsaturation. And the structure of aspirin is shown on the screen, and you'll notice that the 6 degrees of unsaturation can be accounted for by, first of all, you have 1 ring, and you have 1, 2, 3, 4, 5 double bonds. That equals 6 degrees of unsaturation. What about vitamin C? C6H8O6. Once again, neglect the oxygens, pretend they're not there. Compare C6H8 versus C6H14, and you end up with a difference of 6 hydrogens, which is 3 H2s, 3 molecules of molecular hydrogen, which is 3 degrees of unsaturation. And the structure of vitamin C is shown on the screen. It has 1 ring, and it has 2 multiple bonds, the C double bond O and the C double bond C. That adds up to 3 degrees of unsaturation. A molecule called pyridine has the molecular formula C5H5N. Remember, with nitrogen, you remove the N and you also remove one H, and you end up with, in this case, C5H4 for the purposes of the calculation. And I compare that to the totally saturated C5 molecule, C5H12 pentane, and I get 8 hydrogens, which equals 4 H2s, or 4 degrees of unsaturation. And you can see that pyridine has a ring and 3 double bonds in that ring, so that's 4 degrees of unsaturation. Lastly, the neurotransmitter dopamine has the molecular formula C8H11NO2. Well, in this case we have nitrogen, so I have to take N and H away. And the oxygens, I just have to pretend they're not there for the purposes of the calculation. So C8H11NO2 becomes C8H10. Compare that to the totally saturated version of C8, which would be C8H18. That's 8 hydrogens, or 4 H2s, or 4 degrees of unsaturation. And the structure of dopamine, as you can see, has a ring, and it has 3 double bonds, so therefore that's 4 degrees of unsaturation. The most common instrumental methods used in organic chemistry are shown on this slide. NMR, which is probably the most valuable. It gives more detailed structural information on a molecule. Mass spec, which can give you the molecular formula and some structural features. IR, which tells you basically the presence or absence of specific functional groups in a molecule, and UV, which will give you some information about the nature of conjugated pi systems in a molecule. We're going to focus pretty much exclusively on NMR, mass spec, and IR, with a heavier emphasis on NMR and IR. And you're not going to be concerned with the phenomena of this spectral technique or how the instruments work. You know, you're not interested in the physics behind it, but you're going to be given spectral data, and you're going to focus pretty much exclusively on interpreting spectral data to determine the molecular structure of unknown molecules. Spectroscopy in general is the study of how different portions of the electromagnetic spectrum interact with the bonds in molecules. Usually these molecules will absorb that radiation, and there are instruments that can detect the absorption of specific frequencies, and they will print out spectra. And the spectra is what you're going to be focusing on in this course. You're going to be given spectra, NMR, IR, and you're going to have to look for key things in the spectra to help you deduce the structures of unknown compounds. We'll begin with infrared spectroscopy. Before we get into details, take a look at what a typical infrared spectrum would look like. It is marked off in wave numbers at the bottom and wavelengths at the top. It's easy to convert a wavelength to a wave number if you just take 1 divided by the wavelength, multiply by 10 to the 4th, you would get the wave number in reciprocal centimeters. So for example, 1 divided by 2.5, so you can see on the scale here, 2.5 microns equals 4,000 reciprocal centimeters, and so 1 over 2.5 times 10 to the 4th is 4,000. Sometimes this would be helpful because if you get a peak that appears roughly here where the laser pointer is, it's hard to tell from this scale at the bottom. Is that 2100? Is that 2200? 2250? What is it? Well, it's just go all the way up to the top, and you can see that it's 4.5 in wavelength. 1 over 4.5 times 10 to the 4th is about 2200. So it's a good way of getting a more accurate wave number in an indirect way. The spectrum itself is divided up into 4 distinct regions. On the left-hand side, roughly from about 2500 to 4000 is the single bond region, NH, OH, and CH. The region between about 2000 and 2500 is the triple bond region. Between around 1600 to about 1890, 1900 is the double bond region, and then the region all the way to the right is frequently called the fingerprint region. You can get some useful information from that, but In general, you don't even have to do any interpretation in this portion, and we're going to, even though your textbook might describe certain key peaks that you can identify in this region, we're going to be focusing on these other three regions, and you'll get all the information you need to deduce structures just by looking over here and not going into the fingerprint region. For infrared spectroscopy, unlike other types of spectroscopy, you do not have to identify every peak in the spectrum, which is great. All you're doing is you're looking for the presence or absence of functional groups in a molecule. That's the information, the key information you get from infrared spectroscopy is the presence or absence of specific functional groups. And you will see that specific functional groups will have very characteristic absorbances in IR as we go through. Now, rather than memorize a lot of information and also having to refer to tables all the time, I think it's a good idea for any type of problem that you encounter in this course in organic chemistry is to have a method. So for infrared spectroscopy, I suggest the following method. It's shown at the bottom over here. Every time you encounter an infrared spectrum, be methodical. All you have to do is remember to ask yourself 4 questions. The first question is, are there any sp2ch bonds present? The second question is, are there any triple bonds present? And the third question is OH or NH present? And the fourth question is there a carbonyl present in the molecule? And if you answer all those questions, you'll get all the information that you need from the IR spectrum in order for you to deduce the structure of the compound. The first question that you would ask yourself when looking at an infrared spectrum is, do I have any sp2ch bonds present? And again, rather than memorize lots of numbers, there are 2 numbers that are important to remember in interpreting IR spectra, and that would be 3,000 reciprocal centimeters and 1,700. We'll get to 1,700 later, but 3,000, straddling 3,000, you'll see peaks corresponding to CH bonds. Just to the left of 3,000, that is just slightly greater than 3,000, you have sp2chs, and then just to the right of 3,000, that is less than 3,000 reciprocal centimeters, 2990, 2995, 2900, would be sp3chs. That's illustrated in this infrared spectrum of hexane, totally saturated molecule, all sp3chs. Remember, we're not looking at this region down here, the fingerprint region. We're only looking at things, say, about 1,500 and above. It's pretty boring. There's not much going on here, but you do get an intense absorption just to the right of or less than 3,000, which corresponds to the sp3ch bonds. Take a look at 1-hexene. This molecule has both sp2chs and sp3chs. And as you would expect, straddling 3,000, you have on the right-hand side, less than 3,000, you have a large peak corresponding to all of those sp3chs. But if you look carefully to the left of 3,000, that is just greater than 3,000, 3,100 or so, is the sp2ch bond. So when you take a look at 3,000, it's very easy to tell whether or not you have hydrogens attached to sp2 hybridized carbons. Another example of sp2chs would be on a benzene ring. Here you have T-butylbenzene, which has sp3chs and also sp2chs. Straddling 3,000, you can clearly see the sp2chs to the left of, that is numbers greater than 3,000, and then the sp3chs to the right of 3,000, that is just less than 3,000. I also want to point out over here this idea of overtones, these little blippy peaks that you see in the baseline. We'll see them again later. They correspond to very intense peaks that occur at about half the frequency. So this is about, say, 1,600 to 1,800 reciprocal centimeters. So from 900 to 600, there should be some intense absorption. So basically these peaks over here are causing these little blips in the baseline to occur. So it's sort of like if you have a stringed instrument and you pluck a string and you get a sympathetic vibration at some other note. That sort of is happening over here. So I'm going to refer to this later on because you're going to see little blippy peaks and bass lines that are not real peaks. These don't correspond to anything that's absorbing here, but it's just an artifact of peaks that are intense peaks occurring at half their frequency or half their wave number. All right, the second question is, do I have a triple bond present? You can see in this molecule you have a carbon-carbon triple bond, and you have a peak in this region in the red box. And the same thing down over here. You have a carbon-nitrogen triple bond in this region with the red box. Normally this area is a dead zone. It's a desert. There's not much that absorbs here, and if you have a peak that stands out, you can be sure that it's for a triple bond. Take a look at the difference in intensities here. You have a relatively weak bond for the carbon-carbon triple bond, but a much stronger bond for the carbon-nitrogen triple bond. And this is a good time to point out the general feature in all IR spectra is that the more polar the functional group, the more intense the peak. In this particular case, if you have a very intense peak in this region and you have a nitrogen in the molecule, chances are that it is a nitrile, C triple bond N, and not C triple bond C. Also, if you do have a peak, not terribly intense peak in this region, it could be a C triple bond C. Well, is it an internal alkyne or is it a terminal alkyne? So, for example, this would be a terminal alkyne where the triple bond is at the end of a chain, which means that you should have a CH bond. You should have an SP-CH bond, and those are very easy to pick out. They're in the CH region, and they're even further to the left of the sp2CHs. So what I'm pointing at over here with the laser pointer are all of the hydrogens attached to the benzene ring, giving this absorption, and this very intense absorption over here is due to the sp-CHs. So they really stand out. The third question you ask yourself is, do I have OH or NH bonds present in the molecule? Where do you look? You look to the far left. It's the furthest to the left peaks in an infrared spectrum. For example, if you take a look at the spectrum of 2-hexanol, a molecule which has lots of sp3CHs, and you see absorptions for sp3CH here, but it also has an OH, and you have this very big, broad peak, well-defined but broad, that corresponds to OH. NHs also will absorb in this region. Quite frequently they're not as intense, but it's also possible to look at specific characteristics that will help you to determine whether it's a molecule that has 2 hydrogens attached to nitrogen or a molecule that has 1 hydrogen attached to nitrogen. For so-called primary amines, which have NH2s, you end up with a peak which is split. It's a forked peak. Easy to remember. You have 2 NHs, and so therefore you would have these 2 little peaks separated from each other. For a molecule that has only 1 NH, you have a single non-split broad peak in this region. Something else that you have to watch out for, I mentioned overtones before. We have another absorption due to an NH bond, which is close to the fingerprint region at about 1600. So twice the it's an intense peak, so twice the frequency at about 3200, we have an overtone. So, if you do happen to see a forked peak and you have something else that's sticking out to the right-hand side, don't confuse that for anything else. It could just be an overtone. The fourth question you ask yourself when you look at an IR spectrum is, does the molecule have a carbonyl? Is there a C double bond O present? And where do you look? You look at 1700 reciprocal centimeters. That's the second number that you should remember. 3000 is the sp2CH, sp3CH region, and 1700 is around there is the carbonyl region for aldehydes, ketones, carboxylic acids, and esters. These are the four carbonyl molecules that you're familiar with at this point. How do you distinguish between them? Of all these four, the carboxylic acid should be the easiest to distinguish because it's the only one that has an OH. Molecules that have both carbonyl and OH could be a carboxylic acid, but for carboxylic acids, the OH is different than the OH for an alcohol. For a carboxylic acid, the OH peak is huge. It starts way over to the left where a typical alcohol absorption would be, but it actually stretches beyond and below the absorption for sp3 and sp2CHs. So for example, hexanoic acid here has sp3CHs. Here's the absorption for it, but notice that the OH starts way over to the left and it continues and actually engulfs all those peaks and goes below it. So if you have a carbonyl in the molecule and you have a huge OH that smears all the way down into or even below the sp3CH region at around 3000, it's got to be a carboxylic acid. So they're very easy to pick out. If you do have a carbonyl in the molecule, there are two other sub-questions that you should ask yourself. If a carbonyl is present, look to the right of the sp3CH region, and if you do see one peak or two little peaks standing out, that would indicate that you have an aldehyde. An aldehyde is the second easiest carbonyl type to pick out because it's the only one that has a hydrogen attached to the carbonyl. And remember, this is the CH region, so the aldehyde CH stands out just to the right of the sp3CH region. There are actually two peaks that are accounted for by this CH. It's hard to see here, but the one on the right is very easy to pick out. But there's another one that's being pointed out here on the spectrum that's partially buried in the sp3CH absorption, and that's also due to the aldehyde. Sometimes that one is obscured, when you have a longer carbon chain or more sp3CHs, the sp3CH peak is going to be bigger, and it might actually engulf this peak. So sometimes you only see one absorption. In this case, you can actually see two. The second sub-question you can ask yourself is that if you do have a ketone or aldehyde, and the absorption is greater than 1700, it's going to be a non-conjugated carbonyl. If it's 1700 or less, it's usually a conjugated carbonyl. What does that mean? It means that the C double bond O of an aldehyde or a ketone, if it's attached to a C double bond C or a C triple bond C or a benzene ring, if it's a conjugated system, that is the multiple bond of the carbonyl is actually attached directly to the multiple bond of another a structural feature, like in this case over here, we have a benzene ring directly attached to C double bond O, we can say that this is a conjugated system. That means that the pi systems are connected. Notice that this absorption is around 1700 or even just a little bit less than 1700. That's typical for aldehydes and ketones, carbonyls that are conjugated, that is directly attached to a multiple bond. Here's an example of a non-conjugated ketone. This is just butanone, and it has an absorption at around 1715 reciprocal centimeters. So again, this molecule has sp3CHs. I can see them here at less than 3000, and it also has a carbonyl, in this case around 1715. Esters and other types of carbonyl species, that is not aldehydes and ketones, generally absorb at higher wave numbers, maybe 1750 to 1735 or even higher for acid halides. That can be sometimes helpful to distinguish between, say, an ester carbonyl and an aldehyde or a ketone carbonyl. One thing I wanted to point out, important, in the previous slide, I said that if you have an aldehyde or a ketone carbonyl and it's conjugated, that is, it's directly connected to a multiple bond, it'll absorb at 1700 or less. That's only for aldehydes and ketones. So if you have a conjugated ester or say a conjugated acid halide, look at these examples over here. 1726, right? So this is an ester. It's not a ketone. It's not an aldehyde. So therefore, don't expect this absorption to be 1700 or less. So that the idea that if you have a conjugated carbonyl absorbing less than 1700, it must be a conjugated carbonyl. That's only true for aldehydes and ketones. And at the bottom here, I point out that you usually have other information, molecular formula, you'll have NMR information, etc. That'll help you to distinguish between, say, a ketone versus an ester or acid halide functionality. Another type of carbonyl species are amides. That's where you have a carbonyl directly attached to a nitrogen. And that nitrogen could be attached to hydrogens or alkyl groups. For an amide, the nitrogen non-bonded electrons are strongly conjugated with the C double bond O pi system. So therefore, this resonance structure is a very important resonance structure, and you'll notice that this C double bond O will have a lot of C single bond O character to it. And so therefore, the carbonyl will absorb at lower wave numbers. So for an amide, you actually have absorptions at 1700 or less. All right, we'll do some practice problems at this point. You'll see that we have 6 IR spectra. 3000 and 1700 are marked off because it's so difficult to read the wave numbers on these tiny spectra. And what you have to do is match these 6 spectra with 6 compounds from this selection of 8 labeled A through H over here on the left-hand side. Once again, as we go through this, I think it's a good idea for you to stop the video and see if you can answer the questions before the answers are revealed. All right, the easiest way to start this problem of matching is to, the lowest hanging fruit. See if the compounds that would be the easiest to identify would be, I would guess, those which have OH groups. Notice that G is an alcohol and D, it's written in condensed form, but that's a carboxylic acid, CO2H. That's a carboxylic acid. Take a look at all the spectra here and see if you can find one that has an OH in it. Remember, carboxylic acids would also have a carbonyl. G, the alcohol, would only have OH. Of all of these, the only one that has an OH would be this one over here. You can see it. It stands out very clearly. Here's OH. Notice that it does not have a carbonyl. Look, at 1700, there's nothing there. Therefore, of those two, it must be G. So this alcohol matches this spectrum. All right, let's go through this systematically. For this one, take a look and see what you see. Remember, we're not looking in this region over here, the fingerprint region. I'm going to focus over here. There is no OH or NH. There's no triple bond, but I can clearly see at 3000 sp2CH and sp3CH. There is no carbonyl. Don't be confused. You see this over here, and you might think, oh, it's close to 1700, but it's actually a little bit too far away. It's a little bit closer to 1600. And also, look how it's not very intense. Look how there are other more intense peaks in the spectra. Remember, if there is a carbonyl in the molecule, it generally is the most intense peak in the spectrum. So therefore, it's should be easy to eliminate this from the possibility of it being a carbonyl. Now we have a molecule that has sp2CH and sp3CH, no OH, no triple bonds, no carbonyls. Take a look up here. Which one would it be? Well, there's only one really that would match that description, and that would be B. You can see that it has a double bond, so there are sp2CHs, and there's also sp3CHs for the carbon and hydrogens on the ring. Now the one on the upper right, if you take a look at that one, once again we go through let's be systematic. Do I have any sp2CHs? Do I have any sp3CHs? Well, if you take a look just to the left of 3000, there is a little peak here. And so that could be due to sp2CH. There's clearly a lot of sp3CH. The second question is, do I have a triple bond? There's nothing here. So this is a pretty dead region, nothing. Do I have OH? I look over here, I see a little bit of a bump over here. I see this little blip, but don't forget, remember, this is around, I don't know, 3,300 or something like that. At half the wave number, I have a huge peak over here. So this is probably an overtone of this very large peak at less than 1700. So I can ignore it. It's not real. It's an artifact. And don't forget, these are real spectra taken by somebody in a lab, and the compounds could have water in them. And so it's not uncommon to see slight broad peaks over here that might be due to OH. If you have an alcohol or a carboxylic acid, those OH peaks will really stand out. So don't be looking for little tiny blips in the baseline. So I have sp2CH, I have sp3CH, I have no triple bond, I have no OH. I look over here and I have a huge peak straddling 1700. Actually, it's a little less than 1700. What is that telling me? It's telling me that I have a carbonyl, and it's possible that the carbonyl is conjugated. That is, the C double bond O is directly attached to a multiple bond. You take a look over here, which one matches that description? And there's only one, and it would be this one here, C. If you take a look at the structure, it has a carbon-carbon double bond. It has one sp2CH, which would account for the fact that this peak is so tiny. It also has a carbonyl, and that carbonyl is directly attached to the carbon-carbon double bond, causing it to absorb just less than 1700. What about this one over here? This one has a peak which really sticks out. Take a look at the region between 2500 and 2000 in this spectrum, in this spectrum, in this one, in this one, and this one. It's nothing here. It's pretty dead, not much going on. But this one has a peak which stands out very clearly. So even without being systematic, I just quickly look at this, it stands out. I know I have a triple bond in the molecule, but let's go back and do things systematically. Look at 3000. Just to the left of 3000, I have sp2CH. Okay, I see it. To the right of 3000, there are some peaks here too. This is a sp3CH. So the molecule has both sp2CH, sp3CH, no OH, and it has a triple bond. So the only molecules here that have triple bonds are this one, right? This terminal alkyne. I know it's difficult to see, but there is a triple bond there. This is a linear bond, and there's one H attached, so this is a triple bond. And this is also a triple bond. It's written in condensed format. CN would be C triple bond N. So this is a nitrile, C triple bond N, and we have C triple bond C. Which of those two is the correct structure for this IR? Well, we know that there are sp2CHs and sp3CHs. Well, this does not have any sp2CHs. Also, it has an SpCH, and that would be very obvious in this region, but it's not there. So there is no SpCH absorption. This has no sp2CHs. Can't be this one. How about this one? This one has a CH2 group, so there are some sp3CHs, not much, which would account for the tinier peak in the sp3CH region, and it also has a lot of sp2CHs, plus it has a triple bond, and the triple bond stands out, so it's maybe a little bit more intense than you would expect for a carbon-carbon triple bond. So this one must be E. Moving down, take a look at this one. Do I have any sp2CHs or sp3CHs? Well, definitely sp3CH to the right of 3000. There are really no peaks that stand out to the left of 3000. This is just a shoulder of the sp3CH peak kind of curving up over here. So only sp3CHs. Any triple bonds? No. Any OH or NH? Well, once again, this little peak that's sticking out is most likely an overtone of this large peak at around 1700. And at 1700, you would expect a carbonyl. So this molecule has sp3CH, it has a carbonyl, has no triple bond, no OH. The only structure to the left over here that would match that would be this ester, A. Lastly, we have an infrared spectrum, which is frankly pretty boring. We have some peaks in the fingerprint region. We're going to ignore that, but there's not much else going on here except for sp3CH. Again, this over here, this is just a shoulder of this very big sp3CH absorption. There's no OH, no NH, no triple bonds. The only molecule up here, the only compound that would match that would be H. Notice that H, there's not a hydrogen attached to either of the two carbons of the double bond. They're all methyls attached to it. Right? So this shows you that it is possible to have an alkene as an unknown compound that does not have any sp2CHs, and therefore you would not see any sp2CH absorptions in the IR spectrum. Two more practice problems. For these problems, you're given a molecular formula and you're given an infrared spectrum, and you're asked to deduce the chemical structure of the unknown. Normally, you're going to be given more information than this, not just IR and molecular formula to come up with a structure. But for these particular problems, the molecules are so small that once you've identified the functional groups that are present, you have a very limited number of possible structures. So for this one, you can come up with reasonable structures just given this information. Let's start with the degrees of unsaturation. C2H4O. How many degrees of unsaturation is that? Well, again, for the purposes of the calculation, you neglect the O and you compare C2H4 versus C2H6, so that should be 1 degree of unsaturation. Let's look at the IR to see if we can figure out what that degree of unsaturation is. We'll be systematic as we normally are. We start with sp2CH, sp3CH. Do I have any sp2CH? And no, but I have sp3CH. There's nothing to the left of 3000, nothing greater than 3000, but I do see a peak just to the right of 3000. So that's my sp3CH. The second question asks, do I have any triple bonds in the molecule? Now, the answer is no. You don't see anything over here, but actually you didn't even have to ask that question because a triple bond has 2 degrees of unsaturation. As soon as you know that you only have 1 degree, or zero, let's say 0 degrees, you don't even have to look over here. You can skip that question. So you have to remember, you know, the degrees of unsaturation as you're asking these 4 questions. Anyway, that's the second question. The third question is, do I have OH or NH present? Well, I have an oxygen here, so it's possible that this could be an alcohol. But you look over here, and I don't really see anything. Remember, this little blippy peak that's sticking out of the baseline is most likely an overtone of this very intense broad peak at around 1720 or something like that. All right, what is that? Well, that must be carbonyl. That's my 1 degree of unsaturation. All right, so now I can ask myself, well, is it an ester? No, it can't be because there is only 1 oxygen in the molecule. And I know it can't be a carboxylic acid because there's no OH, there's only 1 oxygen in the molecule. So it could be an aldehyde or a ketone. How do I distinguish between aldehydes and ketones? Remember, aldehydes have hydrogens attached to the carbonyl. They have other peaks which arise from the H attached to the carbonyl, and that would be the peaks that you see right over here. These are rather obvious because the aldehyde functional group makes up a very large part of this molecule, so these stand out. Once you know that the molecule has an aldehyde functional group and you know what the molecular formula is, C2H4O, I subtract carbon and hydrogen and oxygen from that, and that would be what's left would be attached, the structural feature that's attached to the carbonyl. So C2H4O minus CHO is what? CH3. So therefore, the only possible structure with this molecular formula and this IR would be this aldehyde. Let's move to the next one. How many degrees of unsaturation do you have for this molecule? And for this one, there are two reasonable structures. Even though it's rather small, there's two possible structures. Let's see if we can come up with both of them. C3H9N. Remember, you have to take N and H away, so that would be C3H8. You compare that to the totally saturated C3 molecule, which is C3H8, and you have 0 degrees of unsaturation. All right, so therefore, I know that I will not have any carbonyls, I will not have any triple bonds, but what I could have is, and let's go through that, sp3ch, no triple bonds, couldn't be anyway. What about OH or NH? Well, there's no oxygen, but there is nitrogen. Take a look on the left-hand side over here. There's a very obvious peak, and the peak is forked. It's split. So that is indicative of NH2. Two hydrogens attached to nitrogen. All right, so take this molecular formula, C3H9N, subtract N and two H's, that leaves C3H7 being the alkyl group that's attached to the NH2. So C3H7 is propyl. And if you go back to what you learned about alkyl groups, particularly propyl groups, you'll remember that there are two types of propyl. There's N-propyl, straight chain propyl, and there's also isopropyl. So the two possible structures for this unknown are this amine or this amine, and you would not be able to distinguish between these unless you had other spectral or chemical information provided to you.